At the end of September, we experienced a significant event in one of our laboratories. A power operator was conducting his late-night rounds in this building, where several labs are located. He heard a hissing noise coming from this lab, so he opened the door and saw significant damage to a floor-mounted fume hood, including broken glass and debris. He shut the door and reported the event right away. We learned fairly quickly there had been a fire in the lab, and became apparent to us that also had been a minor explosion. While the damage to the experimental equipment was significant, the damage to the lab was itself minimal. Over the course of the investigation and the causal analysis, we've learned a lot. We feel it's important to share those lessons with PNNL staff and others from around the DOE complex so everyone can benefit from our experience. Over the next few minutes, we're going to show you a little about the experiment, what we believe went wrong, and what we've learned. As part of the learning, we'll discuss two of the SCoR principles and emphasize how having a questioning attitude and healthy respect for what can go wrong could have prevented this event.
PNNL has been investigating and developing solid oxide fuel cell technology for almost 30 years now. Literally hundreds of cell tests over the years for relatively long periods of time, and have never encountered any problems in terms of any fires or other safety incidents. This is a typical test fixture that was used in the electrolysis tests. The reason that we required hydrogen for the tests was that you have to have a supply of steam present at the cell for it to electrolyze. And the most convenient way to get the steam to the cell in the lab is to react hydrogen and oxygen together within the test fixture. In electrolysis mode, we apply electrical energy to the cell. The cell splits water molecules into oxygen and hydrogen. The oxygen is removed through the membrane of the cell, leaving behind the hydrogen-rich product, which is of value.
For this experiment, house oxygen and hydrogen was supplied in metal tubing at 50 psi to point-of-use valves at the back of the hood. From the point-of-use valves, polyethylene tubing carried the gases to mass flow controllers, where the pressure was significantly reduced to provide 200 standard cubic centimeters per minute of gas to 16 electrolysis cells in furnaces operating at 800 degrees C. Unrelated to the experiment, there were 12 calibration gas cylinders stored in a plastic tote at the back of the hood that became involved in the event also. Late at night, a hydrogen fire started in the hood that did significant damage. It burned the polyethylene tubing that was feeding the hydrogen and oxygen to the electrolysis cells. Flames from the hydrogen valves were shooting out, and as you can see, did significant damage to the hood. Oxygen was also feeding these flames from the leaking valves. The fire burned for approximately an hour and 40 minutes until the house hydrogen supply ran out. During the event, the hydrogen fire overheated and damaged the 12 calibration gas cylinders, causing at least one of them to explode, as shown by this damaged cylinder. The explosion damaged 3 of the doors on the hood, but overall the hood did an excellent job containing the event.
Yeah, so we formed an investigation team. We brought in experts from Oak Ridge National Lab, Idaho National Lab, a fire forensics expert, as well as consulted with hydrogen safety folks from around the country. Well, we definitely eliminated a lot of possible scenarios, but we weren't really able to pinpoint the exact cause of the fire. We did learn an awful lot about how the fire progressed, and we did narrow it down quite significantly to most likely scenarios associated with the hydrogen gas handling system. The supply system of the hydrogen gas that was delivered up to the experimental device was likely the location where the fire began and got more serious.
After the event, we wanted to make sure that we didn't have any other experiments that had similar conditions. So we did a series of extended conditions. The first one, we were looking at experiments that had flammable gases in close proximity to a heat source, and they're also being run unattended. Later on, when we found out that polyethylene tubing was a factor in this event, we also decided to look at experiments that were using non-metallic tubing that were carrying both either flammable or toxic gases, again in a close proximity to a heat source. And then we also wanted to make sure that our storage of gas cylinders, particularly lecture bottles, were being stored appropriately.
A compliant system does not necessarily mean a safe system in an upset condition kind of scenario. So we're looking at now implementing, a number of design features. For example, we were using 1/4-inch tubing and 50 psi hydrogen supply, which was way more hydrogen than we really needed for the experiment. So we could have reduced pressures, we could have implemented flow restrictor orifices, things like that, that would have really reduced the consequences of a failure of one of these lines that we may have had. So this would have been just somebody standing back and asking the question, we're operating this thing unattended for long periods of time, we're using hydrogen, what could possibly go wrong? What should we design into this system to be able to make it fail in a safe manner if something unexpected happens?
The National Fire Code for Laboratories allows for the presence of small gas cylinders in hoods. Yeah, this event would have looked very different with if these gas bottles had not been stored in the hood. It would have probably just been a fire and just some fire damage and not the rupture of the lecture bottle. PNNL Fire Protection is reevaluating the policies and procedures for the use and storage of small gas cylinders in hoods to ensure that none of the operations in the hood are going to put the gas bottles at risk.
This event exposed for us something we call the silos of excellence. It's where our subject matter experts in the area of, let's say, compressed gas safety, pressure system safety, look at the hazards, the requirements, and the control sets in a very vertical, stovepiped manner. We need to address those in a more horizontal way. And to achieve that, we're going to establish a new position called a System Safety SME role.
We really do need to continue to question every day what we do. We've done this kind of work for decades, and this is just a real strong reminder that you do need to have a healthy respect for what can go wrong so that you can adjust for it, correct for it, and ensure continued safe operations.
Again, it was an assumption that things are going to go as planned, things are going to go as we expect, it'll be right. We have a lot of history with that. And so I think that lulled us into a sense of overconfidence.
I think that is something that we always have to guard against is, just always believing we've got it nailed. We should always look for continuous improvement opportunities.
As you take into consideration everything that you've seen, recognize that PNNL in our research, we've been very successful. It's not perhaps even normal to understand and think about consciously what can go wrong. But it's so important to do that. You need to involve others in looking at your research setup, to make sure that they're seeing things on your behalf that perhaps you don't see, even if you've had hours or years of experience with these systems. Perhaps something about those systems is not picked up, and having that other point of view can help you to understand what could go wrong with this system. Thanks for all you do, and stay safe.